Happy post-Thanksgiving, friends. We're going to keep moving on with Ampere's Law. Hope the celebration went well and that you got to spend a little bit of relaxing time. Um, Pretty much by yourself. Bummer for Thanksgiving. But as I seem to find myself saying so much these days, that's COVID for you. So we are in the home stretch, thank goodness. And we're going to go ahead and get started on doing some Ampere's Law examples. So that's what today is about. So let's get started and take a look at a pretty typical, excuse me, situation here, which is going to be the infinitely long solenoid. And a solenoid is just a fancy term for a coil of wire. And how many turns does it have? Well, of course, it has N. It's capital N terms. And it's got, since it's infinitely long, N is also infinite. So what it has is a number of turns per length. So let's think of it as little n. Oh, that is a terrible looking little n. Let's try that again. Since I can't know really how long it is or how many turns there are, then there's little n turns per length. Now, if this was a finite size solenoid, then we'd call it have length L, and then there'd be N over L turns. And we could talk about, just as we did with the parallel plate, we could talk about what's the B field just kind of in the middle and away from the edges. Okay, so we can do that. Excuse me. So here's what we have. I'm going to try and draw a solenoid for you. And now, of course, this goes on infinitely long. And I can see that my density of turns is changing, and I didn't mean for that to happen. But it did. So how are we doing this? Well, you can't really see how I'm doing this, because if I said, oh, look, the current is going this way, well, what does that mean? Well, it means it's going down through that one, and then if you blink your eyes, it has changed to the other side. So what I'm going to tell you is that we're going to look at it from this side, and the edge view essentially looks like a wire. I'm going to give thickness to the wire. It's kind of ridiculously thick, but that way I can draw what's going on. So in this case, the current, I had labeled that. I had not labeled that. Sorry, that's supposed to be I. The current is going around. If I'm looking from that direction, I'm assuming it's going in a counterclockwise manner. So the current in the wire is going like this. That's I. All right. And then you'd question, well, what is the magnetic field then? Well, the magnetic field, if you remember our previous right-hand rule, it was the one in which we have a piece of wire. So we stick our thumb in the piece of in the direction of the current in the wire, and then our fingers are going to wrap to show which direction the magnetic field's going. So if I start at the 3 o'clock side on this diagram of the edge of the solenoid, and I go, okay, well, the current's going up at the 3 o'clock side. So outside the solenoid, it's going into the page, and inside the solenoid, it's coming out of the page. And then I go to 12 o'clock and I go, oh, same thing's happening. If I go this way, then then the magnetic field is in at the top and out at the bottom. If I go to 9 o'clock, the same thing's happening. It's out in the middle, in at the outside. So you see what's happening here is the magnetic field I'll just draw here. It's coming out of the page, and then out here, it would be going into the page like that. That would be B here, okay? And if I were to draw that back here on the solenoid itself, what that looks like is a field within the coils, which is going like this. Okay, that would be the B field inside the coils. And if there were edges to it, then what you would find is you would find the wrapping, right? You would find a wrapping like this. But notice the field density, the density of lines of the field here, very much weaker outside. It's going to go out like this, wrap around, come in. But look at the density of lines. Like this is a very weak magnetic field out here compared to what's going on inside the solenoid. Okay. So for that reason, we are going to concentrate only on the inner field. Okay. So I'll just note that this is a weaker field outside. Stronger field inside. And so we're going to concentrate on that field inside because typically that's the one we're looking for anyway. And also that's why I made it infinitely long, because if it's infinitely long, then the B field can never get out, which is a kind of a funny situation, but kind of like the parallel plates, right? I made them infinitely long. And if you looked at the E field near the center and they weren't infinitely big, then it was kind of like being in an infinitely large charged plate. All right. And actually that approximation holds good for pretty much most of the things. If you ignore the edge effects, right, they're typically kind of small unless you have something wacky going on. Same thing here. The outside effects are going to typically be fairly small compared to the field that you have going on inside, inside the coil. Okay, so what I'm going to do now is I'm going to slice that coil picture. I'm going to slice it and take a look at. So if you take, imagine I've got, so here's my side view picture. I'm going to slice it like right through the diameter vertically. Okay, right through there. And I'm going to redraw that here. So what I have then is a bunch of currents coming out of the page at the top. All right, so here's a, what's it called? Cross section. So here's the cross sectional view. So if I look at the cross section of this thing, I'm going to get a bunch of dots here. All right, I'll try and space them the same as the coils, but I may not actually end up doing that. So just because I need a little bit more room here. So I'm going to space them. I'm just going to go ahead and space them like this, which isn't that far off what I drew. All right, and that goes on that way. And then at the bottom, the current's wrapping around. So I'm going to have the current going in at these points, right like this. Okay. All right, so there's my current. This is I. Okay, and now I'm going to draw the field. The field inside is here. Oops, it's supposed to be fairly straight. Okay. Like I have graph paper lines, why don't I use them? Oh, for goodness sakes. Okay, let's try that again. Yeah, not bad. Frowning at the thing. Get a straight line. All right, so now I have to pick an Amperian loop. All right, so first off, let's take a guess at what I think the B field's going to look like here. The field, like I said, I've already drawn a couple of parallels with the parallel plate. So if this is an infinitely long solenoid and I have only to consider the field inside the coil, then I'm wondering if there is any effect of anything. Maybe there's something due to the size of the coils, but I didn't include a radius of the size of the coils, and I don't know how you'd include that. So, what about well, I guess what about all that outside field? Like that's okay. Well, it's close to zero, but I mean, there'll be, so let's consider this finding the maximum field. But if I'm looking for the field inside, I don't see why it should change, I guess. All right, so let's take a look at an Amperian loop. Um, so my Amperian loop here is going to have to enclose some current, right, as a flux, right? And then it's going to have to circulate with the B field. So this B field, though, doesn't really circulate that much, does it? It seems to be pretty straight. So really what I'm interested in here is that is that field inside the wire, so inside the coil. So what I'm going to do is I'm going to draw myself something that goes along with the B field here. I'm just going to draw myself a rectangle like that. And I'm going to traverse the rectangle with the B field so that I can get rid of that B dot ds shenanigans on the left side of Ampere's law. Okay, so my loop here has something like length little l. Okay, and I have got to think about the two sides just like I have with Gauss's law. So I got the left side, which is going to be a path all the way around my rectangle here. So the loop integral of b dot ds all the way around the rectangle here, that means I got to look at all the sides. All right. But if I consider b to be 0 out here, if I consider b to be weak enough, and I'm not really concerned with it out here, so then I'm going to get 0 contribution from the top side because there's no field there, or that's weak enough that I can ignore it. And then from the two up and down sides, I'm going to get 0 because the B field is perpendicular to the ds. Okay. So even though I cross ds, so I'll draw another B field here. Look, here's another B field line. It's going to cross right past that side of the rectangle. So there's a B and there's a ds as I go down those loops, but the dot product kills those sides, okay, because they're perpendicular. So I'm going to get no contribution from the sides. All right, so here if I look at sides 1, 2, 3, and 4 is the bottom, I get no contribution from sides 1, 2, and 3. Okay, now remember that little circle on the integral sign means I got to go all the way around my loop and back to where I started. It's a race. Okay, it's like going around a little track. So if I start here and I go downside 1, I get no field, so no b dot ds. I go downside 2 and I go, oh, well, b dot ds, I get 0 from the dot product. There's a b and there's a ds, but they're perpendicular. So now I go alongside 4 and that's where I'm going to get my contribution. I go back up side 3 and I'm going to go, oh, b dot ds is 0 again here. All right, so side 4 is the only one that's going to give me an integral of b dot ds. So this really equals, that's 0 for side 1. the dot product is the thing that kills it for side 2. Kills it for side 3. Oops, side 3. Oh, bother. Okay, let's try that again. That's 0, and it kills it for side 3. I didn't really go around in a loop in this case because I wanted to say 1, 2, and 3 are 0 instead of 1, 2, and 4. Okay, and in this case, B is parallel with DS. If I'm stepping along the green loop from left to right, I'm going with the field, so the dot product is 1. B is the size of B. It doesn't seem to be changing because my loop is right on only in one spot, and B is not going to be changing along that horizontal line. And DS is just DS, and so this is going to become B times L for loop 4, for side 4. Okay. Okay, so now I have to look at the flux of current on the right-hand side, which is also called I enclosed. So how much I do I have enclosed in this thing? Well, I've got some number of loops. I got some number of turns. And I had a density of turns of wire, right, per length. Now, you could just look at this, but I'm going to ask you to elevate yourself above this. You could notice I drew a finite number of turns of wire in my Amperian loop. So let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 turns that I enclosed in this thing. Which is, sure, could I do that? Yes, but am I really doing that? No. And the reason is because I could make my Amperian loop any size that I wanted. Okay, remember this is essentially an infinitely long solenoid, so I could make the length L 2 miles long, and then I'd have to go through and count every single one of those loops. I do not wish to do that. So I'm going to write the expression for the number of turns which carry current as flux through the rectangular surface. Okay, so they're coming as they go through the wire, they come out of the page right at the very top, and they go through my rectangle, and then they go down. So I'm counting each one of those times the current goes through the plane of the rectangle, and in this case there's 10 of them. But I want to be a generalist here and say how many, if I have a really large L, how long, how many are they going to be? Well, I don't want to go counting them, so I'm going to say there's little n times little l of them. That's how many turns of loop that are kind of carrying enclosed current through the plane of my rectangle. Number of turns carrying current through rectangle area. All right, and then I got to multiply that by the current because each one of them carries that much current. All right. Okay, so now the application of Ampere's law produces c squared BL on this side for the integral of the loop, and I should get little n little l I divided by epsilon naught on that side. All right. Now, I was getting a little anxious with that little L in there because, it shouldn't matter. The B field shouldn't depend on how long I choose my Amperian loop to be. But here we can see, fortunately, that I'm going to get those things to cancel out. And that's happy days because, like I said, if I chose a 2-mile long loop, then that shouldn't affect the size of my B field inside. Okay, what does affect it is the current. Makes sense. The current generates the B field. And little n, which is the density of turns. All right, so if you got this long spaced out, it's going to have a weaker field. If you got this really tightly packed, it's going to be a stronger field. And that seems to make a bit of sense. So in this case, B is little ni over epsilon naught c squared inside the loop. I mean, inside the coils, right? And we already determined that it pointed left to right. And so there's that left to right. And if you wanted another right-hand rule to think about, instead of using your thumb and then curling like this, instead use the curl of your fingers to be like the current, and then your thumb would point the field. So in this case, the current's coming out at the top, in at the bottom, and the field's going left to right. So if you're having trouble visualizing that, take a look at this picture right here, where the current's going counterclockwise, and therefore the field inside that coil is coming out of the page at you. So that's what your thumb is telling you, right? You're curling from 3 o'clock to 12 o'clock to 9 o'clock, and the thumb is pointed out of the face at you. Okay, so that's kind of like right-hand rule number 4. It's an extension of right-hand rule number 3, or is it 3 or 4? Anyways, it's another way to figure out the current. Look, sorry, to figure out the B field. Look, you have curly and you have straight. Okay, so if you have straight current, use your thumb, and then the curly field is your fingers. If you have a curling current, then use your fingers to be the current, and then use your thumb to be the field, because the field will be straight. Okay, so there you go. And check it out. Is constant. Is a constant field. So this is the magnetic analog to the parallel plate, basically the parallel plate capacitor situation. Okay, I've got a B field that depends only on the geometry of my setup, just like the parallel plate did, right? Just pretty straightforward, a constant field. All right, so let's take a look at another one. Now, in this case, I'm going to go one step further. Oh, one thing I will say about this result, in the textbook, if you read a textbook, you'll find that they use the mu naught. They will use mu naught. So you will find this expression in a textbook, because they use this thing to equal 1 over epsilon naught c squared. Okay. Like I said, I don't need another constant in my life, so I'm going to stick with epsilon naught. All right, now what I'm going to do is we're going to take this and kick it up a notch. And I'm going to take the two ends of my solenoid, or I'm going to take my infinitely long solenoid, I'm going to chop a length out of it, and then I'm going to turn it and connect the two ends. So now I have a donut. All right, and this is known as the toroid. So if I do this, and I think carefully, oof, okay, a little rough. Okay, if I think carefully here, what do I want this thing to look like? All right, it's gonna go like this. All right, you can see the progression. Once again, I've messed up the density of lines. You can see it's changing as I go around. I did not intend that, and that's just an artifact of my poor penmanship. But the idea here is that it's carrying the current. Let's suppose that since this is the top side, the current's going that way, and then it's returning underneath and going around like that. So if we use our right-hand rule, the one we just invented about curly currents, if I go curly current like this, then you're going to notice that my thumb is pointing tangent to the to the circle it's inside. So B is actually going to look like this around the inside. So that's B. It's going to go around like that. Okay. All right, so it's tangent to the circle. Okay. Let's suppose since I had to chop the solenoid, let's suppose that I have in here capital N turns of the wire. Okay, I have to have a finite number of, well, I don't have to have it, but in practicality, I'm going to have a finite number of turns in here. So I have to have chopped that solenoid up. So I have something like that, and I've connected the ends. And so there's a current I that's flowing through this, which I didn't mark, and it's that right there in blank that's going around the outside of the donut. And so what we're going to do is my Amperian loop. Okay, my Amperian loop, I'm just going to follow one of these B fields, right? I'm going to follow a B field all the way around, and it's going to look, I'm going to go in the middle of these two, and I'm going to go around like this. Oops, okay. Whoa, okay, there's my Amperian loop. We need to denote a couple of radii here. That's going to be little r. Here of the toroid, we can assume that something like this is going to be A, something like that is going to be B. Okay. And Ampere's law tells us that c squared loop integral of b dot ds should equal I enclosed divided by epsilon naught. So b dot ds should be pretty straightforward here because b and ds are aligned. If I traverse my green circle in a counterclockwise manner, I'm going to get a ds, let's say right here. My ds is going to be that way. Okay, there's ds. Can't really mark it too easily, but I'll put it over here. There, oops, can't even see that. ds. Okay, so ds is that way. It's tangent to my, if you want to integrate around a circle, you're going to take steps that are tangent to the circle, right? And this B field is tangent to the circle, right? Just as our right-hand rule kind of indicated. So there's going to be zero dot product here. And B and ds, I'm going to assume right on my line, B is a constant value, okay? That may not be true as I make bigger and bigger Amperian loops. And what if I'm way out near the edge here? Well, it's going to have a different B value, I bet you, because the density of turns at radius A is different than the density of turns at radius B. Okay, they can't be the same. So I'll bet you that the field is going to change inside there, but on one green circle, it's going to stay the same value because I'm the same distance away radially at all times. So, oh crap. Okay, hold on a sec. I need to pause. Okay. Did I get you back? Had a little blip in the internet there. So it just suddenly, oh, it switched off. So hopefully I'm continuing from where I was. Sorry if I'm not. It said it was still paused, so hopefully it's okay. Well, I was here. Okay, I'll just hope that everything's okay. All right. So b dot ds around the circle is just the integral of b times, which is a constant, is the b times the integral around the circle, which is just the perimeter of the circle or the circumference of the circle. So this thing here should be c squared b times 2 pi little r. Okay, as we step around the circle, like I was trying to show you over there, my circle goes around like this. I take a piece of ds here, and B is pointed that way already. All right, so all I got to do is follow it around the circle. In this case, I enclosed, if I go all the way around, I had all n turns worth of current. So I'm going to get capital N times I, and that's going to be divided by epsilon naught, like so. Okay, and I don't get anything canceling here, so B is just going to equal the number of turns, the total number of turns of the toroid times the current in them, and it's going to be divided by 2 pi epsilon naught c squared, and there's going to be a little r on the bottom. So it is getting weaker as you go further away from A out towards the outer radius B, and the reason for that is the turn density, the wire density, right? It's kind of like a tighter wrapped solenoid at A, but then it's varying, right? And now you go all the way out to B and it's not as tightly wound. So the field should be dropping in size as you get further out where the turn density is lower. So that makes sense. And in this case, it's counterclockwise around the toroid as I've drawn it here. Okay. So that's, what do you want? I mean, that's good, clean fun right there. That's a toroid. Gosh, I don't have my toroid with me, but I have one. I have a, gosh, I don't remember what the thing was, but I busted open a circuit board at, or an electronic thing, and I yanked out the circuit board, and sure enough, there's this toroid sitting right on there. It's really big and thick. I was like, wow, look at this. So I saved it, but I don't have it with me. I'll see if I can show, or I'll post a picture of it or something. All right, so there's that one. So that's example 2. So let's take a look at example 3 here. Example 3, I'm going to go back to the current in the wire, which I think I'm just passing over here on the left side. Let's see if I can take a look back over here. Ah, look at this. Okay, so I'm going to go back and do this example again. Okay, so let's take a look at it. Of course, with a difference. There's no point in doing it again. You've seen it once already. And you can see it as many times as you want. Isn't that great? Yeah, isn't that great? Yeah, oh, that's great. So here we are in a current carrying wire. And in this time, instead of having a uniformly spread current over the face, I'm going to say that the current density, which you remember is I divided by A, which is a surface, right? Because it's a cross section, not a surface area. It's a cross section surface. Okay, be aware of that. And this is going to depend on the radius. Okay, so let's suppose that this thing equals some constant, like like what? Well, I don't want to call it J naught because that quote, you'll see why in a minute. I guess I could call it J naught, and then we could do this. All right, we'll do it this way. Some constant value times R over A, like that. How about that? Then J naught has the same units as J. And I don't have to introduce some wacky new constant like A or B or something like that. All right, so what does this mean? Here is our current carrying wire. Okay, and the current is coming in. And it's getting, so what this is telling you is there's a little bit here in the middle, and then all of a sudden there's a lot more out here. That's not a great picture, but all right, so it's looking like that. The radius of this thing is A, so that and of course R is less than A here. As you go from 0, which is in the middle where R equals 0, out, then you're going to enclose differing amounts of current. So what I'm going to do is draw my Amperian loop right there. Okay. And what I've done is I haven't really enclosed current. So it's going to be like this, and there's going to be one here, and there's going to be a bunch more like this, and there's one here and a bunch more like this. Okay. So the current that's enclosed through my Amperian loop is changing as I change the size of my Amperian loop. Okay. Well, of course it's changing, but it's changing how much it's changing. Okay. Okay. So, all right, let's take a look at Ampere's law. Oops. All right. Now, I enclosed, this is going to be the same situation as we had for Gauss's law and enclosed charge. When I look at I enclosed, I can't just take a simple ratio. I have to actually integrate the charge density. I had to integrate the charge density. Now I've got to integrate the current density. Okay. So looking at I enclosed, that should be J dot dA, because that's a flux of current density. Remember, that's what Ampere's law really says. It's the flux of current density through the loop. So I need to do a flux integral of the current through my Amperian loop. Now I've got a loop which is in there like this, and it should be following the current around, because as I make my current this way, I'm gonna say, oh, okay, well, I'm gonna be going like this. I'm gonna be curling with my B field. So the B field is going around. If I were to look from the left, it's going in a clockwise manner. And I'm just gonna make those arrows there, which don't really tell you very much because it's a 2D diagram, but it's going clockwise if you're looking from the left, counter if you're looking from the right. Point here is that I've got J dot dA, and J is a function of R. Okay, so here what I have to do is I have to say, okay, well, I'm going to have an integral of J naught R divided by little a dA. Oh, okay, dA. Well, that looks bad. Okay. Thinking. I don't want to change my dA, so let me change let me change the radius of the thing then. That doesn't look bad. I don't want you to integrate little a. Okay, this is now going to be capital R. If this thing will ever write, which I don't know if it will or not. Okay. All righty. Little r over big R. There we go. Dot dA. Okay, so the J naught. So the dot product here is just telling you, okay, what's the flux direction? Now, if I look at the plane of the Amperian loop and I look at the current, the plane has a normal vector, which is perpendicular to it, right? Like that. And the current is parallel with this normal vector, okay? So the dot product should be going away in this case, since we're used to that kind of thing. And then I just need to take an integral, and I need to go around a loop, okay? I like not around like circumference. I mean, like I got to take the area bits inside the loop. Okay, so what I'm going to get here is J naught is a constant and capital R is a constant. Those come out. Integration R. Now, what's the area element of a circle? Well, kind of the same thing as before. If you had trouble doing this, well, what's the area of the circle? Well, the area of the circle is pi little r squared. So just d that thing, and you'll see that you're going to get 2 pi r dr. That looks like dn dr. Okay, so you're going to get 2 pi r dr for your integration. And this means I'm going to get J naught over or 2 pi can come out too. So choose like that. And now I'm going to get integral 1r, 2r, dr. So r squared dr. And I can do that just like I did with the charge density. I can leave that going to a little r like that. I'm going to get a 1/3 r cubed from this thing. 2 pi. Oops, there's a 3 and a little r cubed. So that'll be my enclosed current at little r. And then if I need it at capital R, all I got to do is evaluate little r to be big R, and I'll be all set with it. All right, so now the left side is fairly straightforward. It should just be B around the loop, just like I did with the toroid, exact same situation. B is going right around there with the loop. So I should be getting down here C squared B times 2 pi R. And now I'm going to set that equal to my enclosed current divided by epsilon naught, which is all of this shebang. 2 pi J naught R to the third divided by 3 epsilon naught capital R, like so. And I'm going to drop that thing off with that thing and this thing with this thing. I'm going to swing the C squared underneath. And now I've got a B, which is equal to J naught R squared divided by 3 epsilon naught C squared capital R, like so. And as viewed from the left side, it'd be counterclockwise as viewed from the left. Inside the wire. And remember, this is only inside the wire for R less than capital R, for little r less than capital R. All right. Now, can we be certain that this is going to work at the edge as I start going away from this thing? I'm going to have enclosed the entire current. And so then what I want to do is check this to see if at the boundary, when little r does equal big R, does it equal what I expect? And so we're going to have to take a look at that with the idea of wondering what J naught is. What is J naught in terms of the current? How is that proportional? Well, what I did was I called it J naught equal to the thing that's left over outside of taking a capital R outside. So it's got to be J naught has to be something like it has to be something like I spread over pi, except I had an R, so this should be pi R. No, that's not right. Pi R squared. Well, normally, no, that can't be it. Let's get rid of that. So J naught has the units of current density. See, I fooled myself here. J naught has the units of current density, which would mean that, but I took the R out and made that. Oh, well, that's what you get for making up a problem on the fly. Here's what I'm going to do. Go figure that out yourselves. All right. Good luck. I'll see you later.